What is up, everybody? Today I'm going to be doing the AP Physics 1 exam, um, and the most common FRQ released for everyone. So that's what's going to happen, and we'll get straight into it. So in this question 1, it's a 7-point question, so it's a pretty simple one. Two blocks are connected by a pretty short one. Two blocks are connected by a string passes over a pulley, so it's an add wood machine. And one of the blocks are connected to a spring, K0 constant. It's a spring constant. So the question that they're asking is, I'm going to make it bigger a little bit. The block 2 starts from rest and then speeds up, then it slows down momentarily, comes to rest at a position below its initial position. And in terms of only the forces directly exerted on block 2, will explain why block 2 initially speeds up, and then explain why it slows down to a momentary stop. So, initially, this is the force exerted on block 2. It is the force right here, which is mg, m2g, and it is a force right here, which is tension, right? And it says, in terms of only the force exerted directly on block 2, explain why the block 2 initially speeds up. So this tension force right here, initially it's low, it's not a high force, because this spring, the force of this spring is there's no force on the spring, right? If it's actually like normal in equilibrium, or if it's not released yet, there's no force on the spring. However, as M2 moves down, M1 is forced to move on the right, which increases the spring not the spring constant, increases the force of the spring, which in turn increases the tension on M2. So as the block moves down, oh gosh, this is too big, 10. So as M2 moves down, the tension force has to increase due to the spring, right? And that's pretty much it. And then since the tension force increases opposite to the direction of motion, the acceleration, the velocity, not the acceleration, the velocity must be decreasing to 0. Derive an expression for distance y that block 2 travels before momentarily coming to rest. This is a little bit harder. So first thing that I would do is I would use the energy, right? This is the forces. I would use energy now because we are trying to look for distance. I guess that's not really a good way to explain it. Maybe I'll use forces. So if we were trying to look for distance, we could use a kinematics, right? We could use kinematics. So if you look back here, the forces will be, there's no friction, so that's great. This is the normal force. We don't care about the normal force though, because there's no friction. That's T, and that is M1G, which doesn't count in this equation because M1G is just countered by the normal force. And then of course we have a variable force right here, which is the spring force, right? So spring force would be K0x, and it could be in any direction, depends on where it goes, right? So block 2 is released from rest. Let's read the question. So two blocks connected by a string pass over a pulley. Block 1 is on a horizontal surface attached to a spring at its unstretched length. So if it's at its unstretched length, then initially there's no initially there is not much, I guess you could say, not much force. There's no force on it. So it's actually a better idea to use energy now. because the amount that the spring stretches will be the amount that the mass 2 goes, and I actually digress using forces. I have to use energy because forces will be changing, and if forces are changing, acceleration is changing. If acceleration is changing, it will be a pain in the ass. So yeah, let's do the Atwood machine, and let's do our energies. So first of all, we have, let's put everything in the first. So energy of the spring, right, which is all the initials in one side, all the finals in the other side. So energies of the spring, which is, we'll say, potential energy of the spring, plus energy of block 1, plus energy of block 2, both kinetic and potential. I'm gonna initial plus initial, right, is equal to potential energy of the spring final plus energy of block 1 final plus energy of block 2 final. So it looks something like this. What's the potential energy of the spring in the initial position? 0. There's no potential, no energy. Energy of block 1 initial is also 0. What's the energy of block 2 initial? It's not 0. It's the kinetic energy of block 2 initial plus the potential energy, or I'm not gonna put the triangle. I'm just gonna put Ke of block 2 initial plus Ke of block 2 final. I wouldn't do this, or I'm sorry, Pe of block 2 initial. There's block 2 isn't moving in the beginning. Block 2 has potential energy in the beginning, and the potential energy will come in the form of actually mg delta y, because that delta y is the amount you're gonna drop. Right. So what's the potential energy of the spring final? Yes, they actually do have potential energy final. It's 1/2 k naught delta y squared plus energy of the first energy, the energy of the first mass, which is 1/2 mv squared. But the thing is, right, when it comes to rest, when block 2 travels, when it comes to rest, energy 1, kinetic energy, there's no kinetic energy at all, because it's not moving, right? When it comes to rest, it's not moving. When energy 2, also not moving, so no kinetic energy. No potential energy either, because the block 2 has moved down already. So these two are just gone. There's no more. It doesn't, right? There's no more. No more each of these energies, so we can cross these two out. And then now we can solve the equation by factoring. Move everything to one side first, so 1/2 k naught delta y squared minus mg delta y is equal to 0. So we can pull out a delta y times, you guys can just cross delta y, but that would be thinking too much like a physics student, and I'm pretty sure some of you don't like physics anyway, so I will teach you the math way to do it. Yes, so this is how you factor, like that, and that's equal to 0. The reason why you don't want to divide delta y on both sides is because 0 is also a solution for this equation. So then you have delta y equals 0, but that's not what we want. Obviously, we want the delta y is equal to mg, and mg of what? That's the important thing, because I have to specify whether it's m1 or m2. It's m2, so big M2. So it's m2 g divided by 1/2 k0, and that's your answer. Does the total mechanical energy of the block spring earth system change as block 2 moves downward? It does not, because of a simple thing called conservation of energy. I don't think that's actually sufficient to get the point, but conservation of energy dictates that unless if there is a non-conservative force acting on a system, no energy will be lost from that system. And that is the explanation. It's pretty simple. Okay, that's the first part. We're gonna move this to a new page, and instead I'll probably also move most of my things to a new page. So let's do this. Consider the system. Okay, so it's the same system. It's the same system, and this is US, which means potential energy. Right? I like putting PE because it's better than U. But US and UG. The shaded in bars represent potential energy of the spring, gravitational potential of the Earth system, block Earth system, US, UG, respectively, initial and final states. Positive energy values above the 0 point line, negative energy values below the 0 point line. So these are your energies, initial and final. As you can see, conservation of energy says that all of your gravitational energy has to be converted into your spring energy. But this diagram A right here has negligible friction. This has non-negligible friction. The friction is high enough for us to start caring about the loss of energy. Now, friction does make you lose energy. That's why it's a work by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. So if we follow that formula, or if we just follow intuition, you would know that there will be no gravitational energy. However, we will lose some. We will lose some. We will lose some of the spring energy. There you go. Whatever. So it will be something like this, right? It won't be in the same level as before, but it will be in roughly the same level. So that should be 2 points, or maybe 3, maybe even 3. So yeah, that's the diagram that you're supposed to draw. It's only a 7-point question. This is the next question. Two identical moon A and B, orbit a planet like this. So draw the forces on those. Moon A, planets attract each other. First of all, planets attract each other. So you have to know that because they attract each other, every force will be kind of pertaining to, like, they will be pointing at each other. So you have a force like this, right? They're attracting each other. So in this position specifically, the force, that's one force, that's the force of moon B exerted on moon A. Force of moon B exerted on moon A. And then you have a giant force, a bigger force. It's the force of moon, or, well, actually not a giant force. It should be kind of a little less big, or maybe a little less small, because of the question, what the question's asking. The force of B on planet, exerted by the planet. Or, I'm sorry, A. Planet A. Planet exerted on A. So planet exerted on A. Moon B is a little different. It's like this and like this. So this is force of A exerted on B, and this is force of planet exerted on B. So it'll always be pointing to the direction of the whatever, there is, right? So if it's a planet, pointing in the direction of the planet. If it's a moon, pointing in the direction of the moon. Right, so it'll look something like this. Something like that. Really messy, but good enough animation to have you watch again. Consider net gravitational force. Justify why the magnitude of the net force exerted on moon A could be larger than the magnitude of the net force exerted on moon B. So let's move this up a bit. The magnitude, okay, so the magnitude exerted on A could be larger than the magnitude exerted on B if the radius between A and B, or I guess you could say A and the planet, isn't big enough to counter the effects of the force that moon B exerts, or what is it? Moon A exerts on moon B. In other words, by equation form, it'd be something like the force is equal to the force of gravity is equal to gm m1 m2 over r squared, right? gm1 m2 over r squared. So what I'm basically trying to say is, if the force exerted, if F planet B minus F of AB, if F of AB right here is smaller than, smaller than, so this is big enough. If this is big enough, it will make this smaller than the force of B exerted on A, plus the force of planet exerted on A. And that can only happen if this radius factor is big enough, so that F of planet B becomes smaller, right? Because this isn't really, these are the same. These are the same. They're the exact same, right? The same. So you can't really fix that. The only thing you can fix is these distances right here. So if RA is large enough, then this force will be negligible, and then this force will be more than this force. So if RA is big, I'm saying if RA is big enough, then this happens. So this happens if RA is big enough, right? And that will be great. And similarly, if RA isn't big enough, isn't large enough, then the force exerted on moon B is greater than moon A. Derive expressions. Net force FA exerted on moon A. So this is quite easy, actually. Let's just go ahead and move this back down. Simply, the net force FA exerted on moon A is equal to force of BA plus force of planet A. So that's equal to force of BA plus force of planet exerted on A, which is equal to 1/2, or what's M0 and MP? M0 is each moon, and then MP. Okay, so they're equal signs. So it's 1/2, or I don't know why I have 1/2. I'm sorry, G times M0 squared over RB minus RA. Is it RB minus RA? No, it's RA minus RB. Squared. Plus, plus G times M0 MP over RA squared. That's net force exerted on moon A, and this is the net force exerted on moon B is G times M0 MP over RB squared, minus G m0 squared over RB minus RA squared. So the only way, if you look at these two equations, RA minus RB, I'm sorry, but it really doesn't matter. So if you look at these two equations, you can note that the only way for the equation to actually, the only way for this equation to be smaller than this equation is for RA to be massive, right? Like really, really big. Or else it wouldn't work. So could the expressions in part C support your reasoning in part B1? Yeah. Well, yeah. Because if part B1 is justify that y the magnitude of moon A could be larger than the magnitude of net force exerted on moon B. So and that means this could be larger than this. So if RA is, yeah, I'm just basically going to repeat what I said. If RA is small enough, then force of planet A planet A will be larger than the force, or I'm sorry, smaller than, less than the force of BA, I think, or no, AB, I'm sorry, AB, which means that net force on A is larger than net force on B. And then same thing, if RA is not small enough, then then this sign reverses, so net force on B is larger than net force on A. I hope my reasoning is not flawed. Question 3 is a lab question. I don't like lab questions, but let's go. A wheel is mounted on this axle, a light spring attached to wheel's rim and wrapped around several times, and a small block is attached to the free end of the string. When block's released from rest, the wheel begins to rotate with negligible friction. Different forms of energy change as the block falls. The student says there's a kinetic energy of the block increases as it falls. They say it's because of gravitational potential energy converted to kinetic energy. The student decides to ask whether the decrease in gravitational potential energy is equal to the increase in the block's kinetic energy from when the block starts moving to immediately before it reaches the floor. Okay. Design experimental procedure students could use to compare the increase in the block translational kinetic energy with the decrease in gravitational potential energy of the Earth's block system. Okay. So, quantity to be measured. Symbol for quantity, equipment for measurement. One of the quantities that we should measure is the distance, or I guess you could say, what is it? We have a graph, right? Yeah, so distance. D, right here. D. And symbol for quantity is meters, or quantity is distance, so distance. D, equipment for measurement, ruler, meter stick, whatever. Do we need anything else? Different forms of energy changes, gravitational potential energy, kinetic, converted to kinetic energy. I don't know why. I think we also need speed. Yes, speed. So speed. With a speed. Symbol for quantity would be, or I could just say speedometer. I don't know if that's found in a, or if we don't have a speedometer, then I could say photo gate. Speeds in meters per second, or I could say V and photo gate or speedometer. I guess acceleration is probably better. Is acceleration better than speed? No. Yeah, speedometer is probably more accurate. Speedometer. But the thing is, actually, no. Photo gate. Because speedometers are bad. They're bad for calculating certain stuff. Or I could measure time. Yeah, in fact, I'd measure time. I'm gonna measure time. Is that a good idea? Is acceleration constant? I think it is. So time. So that's t. So that's stopwatch. So what do we do? 1. Setup. 2. So once you have the setup, start dropping it. Actually, first measure the distance from the block to the floor. 3rd, start dropping it and measure time. 4th, do that for multiple times. 5, start measure a unwind, I guess you could say, or unravel the string and start it from a different distance. 6, measure that time. 7, repeat. Repeat part 4. 8, repeat part 5. And repeat parts 5 through 6. Right? And then we keep going. 9, keep repeating part 7 and 8. Or I guess we could say like that. Part 4 through 6, and then keep reporting part 7 until you gather enough data points. And I think that's it. So, I mean, yeah, I don't need a diagram, but I'm going to show a diagram. So, in the beginning, it will be something like this. Right, and then you have a string like this, right, and you want to measure this distance, and then you'll do that multiple times. You'll measure the time and the distance, and then and then maybe you want to do it a little bit lower, right, and then you measure this distance, and then you drop it, and measure the time. I'm pretty sure the time is constant, or the acceleration, I mean, is constant. So let's go to the next one. Is there a B? Yeah, there's a B. So the graph above represents both the change in gravitational potential energy and the change in kinetic energy, translational kinetic energy gained by the block. So you have to draw a line or a curve that represents the rotational kinetic energy. So rotational kinetic energy plus translational kinetic energy equals gravitational potential energy. And how do I know that? I can put all the kinetic energy initials, all the energy initials. You would have no potential energy, or you will have no kinetic energy initial, and you'll have no potential energy final. So, excuse me. So the rotational kinetic energy will be something like right here, and we'd have to draw a line, which I'm going to ultimately fail, but I'm going to try. Something like that. That actually went a lot better than I thought. So something like that, right? Just make sure that the two things that you drew have to add up to this bottom right here. function of time following distance d. Okay, so yeah, it's the same thing. So the students measure an angular velocity of the wheel like that, and draw the okay, rotational kinetic energy kr of the wheel, as shown below. Draw a straight line that best fits the data. That'll be hard. That'll be hard with my. I did okay. I actually did pretty good. Yeah, something like that. I don't care. I'm not a perfectionist. So let's do like this, and like right here. Actually, those are two terrible data points right here and right here. So it'll be something like 0.8 minus 0.4 joules over. Alright, this is the slope, so you have to find the slope. 0.8 minus 0.4 joules divided by 25 minus 10 rad squared per second squared, so rad per second squared, which is equal to 0.4 divided by 15, which is not a fun number. 0.4 divided by 15 is 0.04 divided by 1.5, 0.0267. 0.0267 joules over rads per second squared. So what do you do now? Well, if we want a y equals mx line, we'd have to find that the kinetic energy of your wheel, the rotational kinetic energy, we have to know that it's equal to 1/2 times I times w squared. This is in your formula sheet, I think, so you should already know that. So if this is to serve to be your y, and this serves to be your x, then here is your slope right here. So y equals mx, that's your x coordinate, it's w squared, and y is kr. So 1/2 I is your slope. So I is your rotational inertia. I is 2 times the slope, which is your rotational inertia. It's 0.534 joules over rads per second all squared. And I think that's it for this question. Okay, yeah, that is. Student has clay and a rubber sphere, both of the same mass. Right, both objects thrown horizontally at the same speed. In A, it sticks. In B, the rubber sphere bounces off after the collision. So in the figure above, the arrow represents the momentum immediately after the collision for the clay block system in case A. And in the figure to the right, draw an arrow starting on the dot to represent the momentum of the sphere block system immediately after the collision in case B. If the momentum is 0, write 0 on the dot. It is not 0. It is the same momentum. Absolute same momentum. Because of conservation of momentum. And it's the exact same length as well. So there you go. After the clay and block A collide, block A lands dA. Does block B land a horizontal distance from the edge greater than, less than, or equal to dA? In a clear, coherent paragraph length response that may contain equations and drawings, explain your reasoning. So this is hard, or well, it's not that hard, but let's see. So block A, the clay and block A exhibits a or a velocity, a final velocity that is equal to what is it? Clay block. Okay, so I'm just gonna make the equation. So it'll be m clay v clay is equal to m, or I say v naught is equal to m clay plus MA V final. Right? Which means V final is equal to M clay V naught over M clay plus MA. Alright, so when you see this equation, according to this equation, M clay, or the velocity final, is affected by the mass of block A. Right, is actually inversely proportional to the mass of the clay plus the mass of block A. And this decreases the velocity final. So if the block of it, right, if by the mass of block, the velocity final of, I'm going to say the velocity final of block A and the clay is affected by the mass of block A and the clay, and so this decreases the velocity of the final. But we only care about block A, so in fact I'm going to remove the clay right here. So it will be the velocity final of block A is affected by the mass of block A and the clay. This decreases the velocity final accordingly. So if the ball then has no mass, if the ball then bounces back, then the velocity final of block A will not be affected by the mass of block, or by the mass of the ball, and so naturally the decrease in velocity is not as is not as strong, is not as big, large. There you go. Additionally, the ball changes momentum in the opposite direction, and to compensate for that, the momentum of to compensate for that, according to the Li equals Lf, or conservation of angular or linear momentum, the momentum of the block has to be greater than the one in situation A in order to be equal to the momentum in situation A. There you go. It's like when it bounces off, first of all, when these two stick together, they're gonna have momentum this. But when this bounces off, it's gonna have like this momentum, right? And you have to compensate for that by having a bigger arrow right here. So you could kind of, counteract that. So the net force will be like this, which would be the same as this, right? So that's a little bit weird, a little bit of a weird thing to keep your head around, but we have these are vector quantities, so if they counteract each other, you have to not add them, but you have to take into consideration which way they point and then subtract them, or do cosine and sines with them accordingly. So let's make a new page, a new page, find page F. Okay, thank you. Okay, final one. Unknown spring constant KO. Okay, lightweight hanger is attached to the lower end of the spring like that. Bottom hanger is 1 meter. Okay, 0.5. kilogram object is placed on the hanger and allowed to come to rest at an equilibrium position. The spring is then stretched downward a distance d naught from equilibrium and released a distance time t0 released at time t0. The motion detector records the height of the bottom of the hanger as a function of time. Output from the motion detector shown in the graph on the following page right here. So what's the spring constant? Spring constant is dictated, or one of the graphs you can use for spring constant is T is equal to 2 pi times the square root of m over k. K is your spring constant, so K is equal to T over 2 pi squared, right? T over 2 pi squared over m, like that. Or simpler, yeah, T over 2 pi, and then you square it, and then you flip, and then you put the m. So m is what? 0.5 kilograms. So m is 0.5 divided by t is 1.25, which is the period. So this is a period. It's bottom to bottom or middle to middle. Bottom to bottom is a period, divided by 2 pi squared. So let's check what that is. That is 0.5 divided by 1.25 divided by 2 pi squared, which happens to be, I happen not to believe that that is the number. Yeah, that is not the number. I need to fix a little bit. So 2 pi squared, 12.63 newtons a meter. At time 0.75, the object spring Earth system has total kinetic energy KO and potential UO at 1.13. Same thing. So explain how a feature of the graph indicates that the total kinetic energy of the system is the same at these two times. So 0.75 is about right here, and 1.13 is about right, where is it? Right here. So explain how a feature of the graph indicates that the total kinetic energy of the system is the same at these two times. So the distance, or the total kinetic energy, is equal to the total energy minus the potential energy. Potential energy, total energy is always constant. So the KE is dictated as a function of P. P, or U0, right? So all the K zeros you should substitute with U0. So PE is the same, or I'm also answering question 2 with this as well. So PE is the same for these two times because the distance from the center, the distance from the equilibrium position of the graph is the same for these two times. Specifically, yeah, therefore KE is the same for these two times. So explain why total potential energy of the system is the same in these two times. So potential energy is equal to 1/2 or 0.5 kx squared, and in this graph, x is the height. In this graph, x is the height from the center of the wave. So in these two times, the wave is or in these two times, the positions and the distance from the center of the wave are the same. The distances, even though they are opposite directions from the center, even though they're opposite directions, the square negates it. There you go. So the experiment is repeated with a spring constant 4, now 4k0. Determine the new equilibrium position above the motion detector. So what was the equilibrium position right here? It was 1 meter. Okay, 1 meter was the equilibrium position. Wait, but it was 60 centimeters here. Let's see. 1 meter is not the equilibrium position. So when he put a 0.5 kilo object on the hanger, it becomes 0.6 meters. So the equilibrium position became 0.6, right? 0.6 meters when a 0.5 object is placed onto it. So basically what it's saying is kx is equal to mg, because mg is this and kx is this, right? And 0.4 mg is equal to 0.4k. So we had a k that was 4 times stronger, which is equal to, I'm going to say 4k times x. So x is equal to 0.4k divided by 4k, which means that's equal to 0.1. So 0.1 meters is your new position, not the new equilibrium position, but the new I guess I'll put the work right here. So mg is equal to kx, right? So mg is equal to 0.4k, but mg is also equal to, now we have 4k times x, or x new. So 0.4k equals 4k, so x is equal to 0.4 divided by 4, 0.4k divided by 4k, which is equal to 0.1 meters. And then 1 minus 0.1 meters is 0.9 meters. So that's your new equilibrium position. Why is it 1 minus 0.1? Because 0.1 is just the distance. So when this was pulled down even more, right, with the block, this distance was 0.6, because the motion detector measures from the bottom to the top. So it's 0.6, which means this distance right here was 0.4. Right, the distance that it was from the original position to this position was 0.4. However, if we had 0.1, right, if this became 0.1, then the distance that the motion detector would measure is 0.9, like that. Object is again pulled from the same distance. On the following graph, draw a curve representing motion of the object after it's released. So, yeah, our k constant is a lot heavier now. So how would that affect all of our variables, the amplitude, the specifically the amplitude and the frequencies, right? the amplitude and the frequencies. So the period is what I'm going to use. Actually, yeah, the period. So t is equal to 2 pi integral, not integral, square root k over m. So we have 4k in there. What are we going to get? That's equal to 2 pi times square root of 4k naught over m, which is equal to 4 pi times the square root of k naught over m, which means this is 2 times t naught. 2 times the initial t. It is pulled down the same distance, d naught. And because it's pulled down that same distance, it's going to oscillate. It's going to oscillate, and I actually think that that's actually a really, really high oscillation. So initially it oscillated 5 centimeters, right? 5 centimeters. But we know that our equilibrium position, right, our d naught pulled down the same distance, d naught, our d naught is 0.4 meters. It pulled down 0.4 meters. So if it pulls down 0.4 meters here, and our equilibrium position is 0.9, or actually, I'm sorry, this was pulled down 0.45 meters. 0.45 meters. So so this is d naught, right? This is 4.45 meters. So if d naught is the same 0.45 meters, then this will be 0.55. Our equilibrium will be 0.9, and then or I'm sorry, not 0.55. No, yeah, it is 0.55. Never mind. 0.55, 0.9, and 1.25 will be up here. Right, so this will be our moves right here, and the period will be double. So since the period is doubled, we're not even gonna make an entire, or I'm sorry, it's not k over m, it's m over k. I did it wrong. It's m over k. It's m over k. It's not doubled. It's halved actually. So m over k. So this would be m over 4k naught. So this would be pi times m over k naught, which is 1/2 t naught. So it's halved, right? It's halved, which means every 0.625 seconds will be one period, which means my graph will be really bad. Maybe I should practice, but I'm not gonna practice. So the graph will look something like that. So one period of the graph will be look something like this. I can't even hit the, I can't even freaking hit the, there you go, something like that, something like that, something like that. There you go. 0.6, or make sure your period is t equal to 0.625. It has to be obviously sine wave, but t equals 0.625. Don't make sure that your graph doesn't look as bad as mine's, and then you'll be fine, right? I'm using a mouse. You guys have your pencils, so you guys, I hope you guys can make a graph that looks better than mine. And that's it. That's it. That's the questions for AP Physics 1. I hope you guys did well on your test. I hope you guys did not fail and did not skip any questions. Most important thing, you can always get a point from guessing and explain about other crap, and you can still get a point. So make sure you do that instead of guessing. It's too late now for me to say it, but in future exams, keep that in mind. And I'll see you guys next time.